Hello students, today we are going to discuss the topic series diode configurations. In this topic we will learn about the simple series diode circuit definition. We will define it. We will discuss some assumptions which is needed to solve simple series diode circuits. Before discussing the simple diode circuit, we will recap the semiconductor diode electrical models, that is ideal and practical, which is needed useful for solving the numericals based on series diode circuits. Then we will have one discussion on source notation, that how the voltage source is denoted. It is also a very important concept while solving the numericals of the series diode. And in last we will solve the series diode configuration circuit step by step and see what approach we will follow. And in last we have the quiz based on our discussions in the test your knowledge session. So let's start with the assumption. So first assumption is that normally the resistance of the diode, which is usually very small in comparison to the load resistance. Normally we ignore the resistance of the diode in comparison to the resistance of the load resistance. So if we define the series diode circuits, this is a simple series diode circuit. We have the diode D1 in series with an E voltage source and the resistance R. So our circuit is said to be series diode circuit if the diode is in series with the input voltage source, or the current which is flowing through the input source is same as the current flowing through the diode D1. So we can define the series diode circuit in such a manner. Now before this we will now discuss the equivalent models. We will briefly summarize the models. We have the two types of models, semiconductor models. One is simplified equivalent models. In this model we will have the equivalent circuit of the silicon as a cut-in voltage is 0.7 volt. If the diode is on, we say if the diode is said to be on when voltage across the diode is more than 0.7 volt, it is said to be in on state, and it can be electrically replaced by a battery of magnitude 0.7 volt with positive and minus voltage. Please mind the polarity. Now when the voltage across the diode is less than the cut-in voltage at 0.7 volt, it is replaced by a diode. It is replaced by the diode by a open circuit. Now we have the another model that is called as the ideal equivalent circuit. In this model we have the cut-in voltage as 0 volt. So when we say that if the cut-in voltage or the voltage across the diode is more than the 0 volt, or we can say more than is positive, then it is replaced by the short circuited. And if the voltage across the diode is less than 0 volt, or voltage across the diode is negative, it is replaced by the open circuit. So open circuit means something which assures that the current is always 0 but the voltage will always exist, while the short circuit tell me that there is always a 0 voltage drop across this terminal, but there is always a current depending upon the surrounding network conditions. Right. So next we will start with the source notation. So source notation, we have the two sources. We have the positive voltage source and the negative voltage source. Here you can see that a voltage source of 10 volt can be represented by the simple dot E is equals to plus 10 volt, and negative voltage source is noted by the minus 5 volt, in which the positive terminal is connected to the ground and minus terminal is connected to the network. So if we take the previous circuit of the series diode circuit, so we can see that this can be equivalently make in 3-step process. First we will make this voltage source to be connected to the ground and this resistance to be connected to the directly ground. This is the equivalent model. There is no change, there is no difference between these two circuits. This is another way of representing the circuit. Now there is a square box we have replaced. We will going to replace this voltage source by a source notation. Using source notation we are going to replace it by the simple dot notation, and this is the dot notation. We have used this simple dot notation, we have replaced the circuit. So we can say this figure and this figure is equivalent. There is no change. This is another way of representation of the circuit, series diode circuit. Now in the next circuit, we have the approach for solving the, what are the approach, how we proceed with the solving the series diode numericals. So first we will mentally see whether the diode is in on state or off state by seeing the network conditions, by seeing the voltage source, by seeing the flow of the current which is making the diode forward bias. So decide the state of the diode mentally, whether it is in the on state or off state. If in some circuit, if you are not able to decide the state of the diode, then assume that the diode in any one state and solve the numerical. If you find the voltage across that diode to be satisfied, then your assumption was correct. Otherwise you have to change your assumptions. So mentally you have to replace this diode by you have to determine the state of the diode. After determining the state of the diode, you need to replace it by a equivalent circuit of the diode. The equivalent circuit, we know that for the silicon diode it is replaced by a 0.7 volt battery. So it is minus VD plus minus VD. So in the on state it is replaced by the 0.7 volt battery with positive terminal connected to the input voltage source and the negative terminal is connected to the load resistance. Once we have the electrical equivalent circuit available, we can apply the KVL, and we can apply, after applying the KVL in the loop, you will get the equation of the current and voltage. You can see that if we apply the KVL, it is plus E minus VD minus IR is equals to 0 and I is equals to E minus 0.7 by R. Since VD is equals to 0.7 volt, so we can solve this and find the value of the resistance voltage into I into R. After solving this, we know all the unknown parameters, that is I and VR. So this is to make sure you should check at the last that the voltage across the diode should come out to be more than 0.7 in this case, or it should satisfy that the assumption which you have taken that diode is in on state must satisfy the voltage conditions. So let us take some example. This is the example. This is the circuit we have, in which we have the voltage source E1 is equals to 10 volt. Here the source notation has been used in series with the resistance of 4.7 ohm, in series with the silicon resistance. We have the 2.2 kilo ohm, and then we have the voltage source of minus 5 volt. So you have to determine the current I and voltage across the resistance R1, voltage across the resistance R2, and the output voltage as denoted in the circuit diagram. Right. So in this we have the on state. On state is we determine that normally the left side we have the E1 is equals to 10 volt and at the right side we have the minus 5 volt. So normally at the left hand side the potential is more than the right hand side potential. So it makes the condition diode to be on state. So in next step we will replace the diode by its equivalent circuit. We know that silicon model has its own equivalent circuit, that is your 0.7 volt, and this is your simple diode. So if you see that this, if I use the source notation, this is the equivalent circuit. This is the diode we have replaced with the 0.7 volt battery. We have the plus 10 volt battery, so it is the positive terminal is connected to the net resistance R1 and the negative terminal is connected to the ground as the source notation, as per the source notation. And we have the another source, we have E2 equals to minus 5 volt, in which the negative terminal is connected to the resistance R2 and the positive terminal is connected to the ground. So this is the equivalent circuit you can see, and once we get the equivalent circuit, we can apply the KVL in the input loop and the output loop. So to find the value of current and voltage and V1 and V2. So if we apply the KVL, you can see in the loop 1 KVL is we can apply, this is the current equations. We have the voltage applied, that plus E1 minus I into R1 minus 0.7 minus I into R2 minus 5 is equals to 0. So if plus 5 is equals to 0, sorry. So if we replace the battery by the values, that 10 minus I into 4.7 minus 0.7 minus 2.2k into 5 is equals to 0. So I is equals to, so after solving we will get I is equals to 2.07 milliampere. Similarly, we apply the KVL in the output loop. We know the value of the current I. So VO minus is equals to I into R2, I into R1. We have the I value is V1 is no. We are finding the value of V into I1, and we are finding V is equals to I1 and V2 is equals to I into R2 when V1 is equals to 4.55 volt. So these are the final value for the circuit. Now we will apply the KVL in loop 2. You will find that what is the voltage, output voltage VO. So output voltage is something, VO is equals to minus 0.45 volt. So let's discuss some simple question depending upon what we have learnt in this lecture. This is the diode circuit, which series diode circuit is given to you. By observing it, what do you think, what is the state of this diode, whether it is on or off? Can you decide it? Also determine the value of the current ID and VO using the series diode configuration equivalent circuit. So let's discuss the solution. This is the solution we have. By observing, we have seen that this diode is in on state because in the node A, if I denote it the left side as a node A and node B, at node A we have the less potential and node B we have the higher potential. 0 is more potential than the minus 5 volt. So after this, once we know this diode is in on state, we replace the diode by a battery 0.7 volt and source notation by a plus 5 volt. Then we apply the loop from ground to ground. It is ID into 2.2k plus minus ID in 0.7 volt plus 5 volt. So this, after solving this equation, you will get the value of the diode current, that is ID is equals to 1.95 milliampere, and output voltage to be minus I into 2 kilo ohm. So V output is equals to minus 4.3 volt. Hope you enjoyed my lecture. Thank you.